Hello friends, welcome to Susan and John MathTube. In this video, we are going to learn something called curvature and of course radius of curvature. Now, I want you to imagine a railway track, or you can imagine any road that comes in your mind. You know that roads keep on becoming what you call straight, and then it will be curved, it will go up, down, etc. etc. Anyway, right now I am interested in bending of curves. How do you define this bend? Or how can you say that I want this much bend in the road, or I want the road to be little bit bent, or I want a big curve or a big bend in the road? So how do you define that? And that is exactly done by curvature. So the first point I want you to understand is, in curvature we are studying about the bending of a curve, or we are rather going to learn about a measurement for bending of curve. I'll show you one curve. Okay, so you can see that there is more bend at this point, right? At this particular point the bend is a little bit more, and again at this point there is a little bit bend, and now you can see there is a bend in the other direction, and at these points there is not much bend. The curve is becoming more straight. I want you to imagine, look at this, I'll show you one point where the curve is bending. Now I'm going to compare this with a circle, and what I do is I choose a circle in such a way that that circle will perfectly fit inside the curve. I'll repeat, I'm going to choose a circle in such a way that that circle will perfectly fit inside the curve. And if I am able to do that, if I am able to select a circle like that, then that circle will be called the circle of curvature. The center of the circle will be called center of curvature, and of course the radius of the circle will be called radius of curvature. And you can see that the bend might be above the curve and below the curve. I think you might have learned about convex and concave curves in your class 11 or class 12 calculus. So based on the concavity and convexity, the circle might appear above the curve or below the curve. So you can notice one more thing. When there is a huge bend, just imagine a curve bends like this, then we will be able to plot only a small circle. At the same time, if the bend is a little bit bigger, then what happens is the circle will also become bigger. So what I want you to notice is, when the curvature means bending, when the curvature is less, when the bending is less, then the circle becomes bigger and bigger and bigger. So look at this, here the curvaceous is very high, at the same time here the curvaceous is very less. You can see it's almost like a straight path. So if I try to make a circle here, the circle will be too big, it won't fit my screen. At the same time here you can see the bending is very high, the curvature is very high, so the circle will be small. So point number one, in curvature what we are studying is, we are studying about bending of curves. We are trying to develop some measurements so that we can measure the bend in a curve. Now curvature shows us how much bend will be there in a curve at each and every point. Now in curvature what we do is, we compare the bend with a standard circle, because you might have learned that a circle doesn't have any points. For example, we know the triangle has like 3 vertices, 3 points. So circle is the pointless figure, so we assume this is the best curved picture. So what we do is, we compare the bend at each point with a circle which will fit perfectly inside that that bend, and that circle will be called circle of curvature, center will be called center of curvature, and of course radius will be called radius of curvature. In some books they define like this: they draw the tangent here and then they draw the inward normal in such a way that the length of the normal will be equal to the radius of the circle. So if you are able to design a perfect circle that will suit the curve, that will suit the bend, that will suit the curvishness, then that circle is called circle of curvature. And one more thing you have to notice: when the bending is high, the circle will be small. And if there is very less bending, that means if the curve becomes more or less straight, then the circle will become bigger and bigger and bigger. Or in other words, the circle which corresponds to the curvature of a straight line will be infinite in radius, because the circle will be so big, no one can make that big circle. So that means the radius of curvature will be infinite. Okay, now I'll tell you one more definition. So let's say we have a curve like this, I have a particular point. Okay, I'll draw the tangent at that point and mark the inclination of the tangent as psi. And I'll take another point nearby and I'll make the tangent at that point, and I'll get something little bit more than psi. Now you can see that when the curve moves from point 1 to point 2, there will be some change in the angle. There will be some sort of change in the angle. So basically, curvature denoted by kappa, kappa is the Greek alphabet, curvature denoted by alpha is nothing but study of change in that angle with respect to change in curve. So that is, we are studying how the angle keeps on changing when we move from one point to another point in a curve. And at the same time, radius of curvature will be inversely proportional to the curvature. That I told you earlier, when curvature is very high, the circle that we can create will be very small, and hence the radius will be very small. So when curvature is very high, the radius will be very small. So they are inversely proportional. At the same time, you can imagine a curve like this. You can see that the curvature is a little bit higher than this. Here the curvature is very high, that is why I told you the circle will be very small, the radius will be very small. At the same time, here the circle of curvature will be very big, isn't it? And hence the radius will be bigger. So curvature and radius of curvature are inversely proportional. Okay, so our radius of curvature is defined to be ds by d psi. Okay, anyway, in your examination, they always ask, find the radius of curvature. Okay, before we start the chapter, let me tell you, in this chapter, you should be very good with Cartesian system, parametric form of a curve, polar coordinate system, and pedal equation of a curve. So you should be very good with these four concepts: Cartesian system, that is a regular system, our xy coordinate system. Parametric system I will explain in a minute. Polar coordinate I will explain in the next video, and same thing with pedal equation. So the questions will be related to Cartesian, parametric, polar and pedal. And sometimes when I check the question paper, I saw that they even ask, find the pedal equation. That means they will ask you to convert Cartesian equations into pedal equations, or maybe even polar equations into pedal equations. So the questions that we interested are finding radius of curvature, of course in Cartesian form, parametric form, polar form, pedal form. And another type of question that they can ask is, they will ask you to convert Cartesian equation into pedal equation and polar equation into pedal equation. And that is exactly what we are going to do in the next 2-3 videos. Okay, so let's start with the formula. Anyway, the derivation is not in your syllabus, so let's start right away with the formula. Please note these things. So look at this, please mark Cartesian system. Now, Cartesian system means our regular system. That is, every coordinate will be measured with respect to the origin by measuring the distance from the x-axis and the y-axis. Of course, you know that. In Cartesian system, the radius of curvature is given by 1 plus y1 square, the whole power 3 by 2, the whole divided by y2. Now look at this. Y stands for the function corresponding to our path or the curve. Maybe the function will be sin x, maybe the function will be cos x, or maybe it's a parabola. So it can even be in implicit form, f of xy is equal to some constant, or maybe in explicit form, that is y is equal to something. And y1 stands for the first order derivative, and y2 stands for the second order derivative. Now, if you want the radius of curvature at a particular point, then all you have to do is you have to plug in that. They will give you, they will of course mention that point in the question. For example, they will ask you what is the radius of curvature at h comma k. So what you do is you just find our radius of curvature in general, and finally you plug in x is equal to h and y is equal to k. So remember, the formula for radius of curvature in general means it can be at any point on the curve. Look at this, in a curve there will be infinite number of points, right? So this formula gives you a method to find the radius of curvature at any point on the curve. Now, in some problems they will ask, find the radius of curvature at 3, 5. So all you have to do is, you have to find the radius of curvature and finally plug in x is equal to 3 and y is equal to 5. Okay, now the second thing I want you to write is in parametric form. Okay, now look at this. Parametric form is a very useful and a very interesting thing. Look at this. When I write x square plus y square is equal to 25, I think you know that this represents a circle with center origin and radius 25. And the equation works on the principle, or the equation is actually a rule satisfied by every point on the curve, right? That is what you learned in your very younger classes. Equation x square plus y square equal to 25 is a rule satisfied by every point. For example, there is a point called 5, 0. Look, 5 square plus 0 square equal to 25. There is another point, what you call 3, 4. 3 square plus 4 square is equal to 25. There is yet another point 0, 5 minus 3, minus 4. So there are millions and millions of points which will balance this equation. And that collection is called an equation. And of course, this is called Cartesian equation. Now, in parametric form, what we do is, we write this x and y as a coordinate. with the help of a third variable. I'll give an example. If I write 5 cos theta, 5 sin theta, then do you know what happens? It will generate the same points which is described by this equation. For example, if I plug in theta is equal to 0 degree, I will get 5 into 1, 5 into 0, that is 5 comma 0. If I put theta is equal to something else, I will get 3 comma 4. If I put theta is equal to something else, I will get 0 comma, actually if I put theta equal to 90 degree, I will get 0 comma 5, this particular point. If I put theta is equal to 180 degree, I will get this point. Like that, now what happens is this theta will generate every coordinate in this circle. So parametric form actually generates all the points in a system. Okay, so remember, a parametric form will always be like x is a function of maybe theta or maybe t or maybe u, okay, and y is another function in t. Okay, so suppose they give you a question in parametric form, then the radius of curvature is given by x dash squared plus y dash squared the whole power 3 by 2 the whole divided by x dash y double dash minus y dash x double dash. Okay, now one advice. Some students always complain that why should I study all these formulae? For such students, I have one good news. If you are 100% good in differentiation, then this one formula will help you solve Cartesian problems as well as parametric form problems. I am warning you, if you are good in differentiation, then you don't have to study the second formula. By the way, if you are a little bit weak in differentiation, I will strongly suggest follow this formula. Okay, anyway, before I wind this first video, let's do some simple questions in radius of curvature. So are you ready with your pen and paper? Okay, please note the first question. So please write, find the radius of curvature at any point on the curve y is equal to a log, by the way, when I write log, I am implying natural logarithm, a log sec x by a. I think we should do it in the proper way, right? Okay, so let's write a log sec x by a. Okay, so it's very easy. Question number 1, is this Cartesian equation or parametric equation? Of course, Cartesian equation. See, it's a relation between x and y. And to be more precise, this is an explicit function. Y is completely given in terms of x. So I am going to write the radius of curvature at any point is given by 1 plus y1 square the whole power 3 by 2 the whole divided by y2, and of course I'll keep it in a box. So you know my aim is to find y1 and y2. So y1 means the derivative of y with respect to x. Okay, before we start, let me ask you two questions so that it will be easy for everyone. What is the derivative of log x? Isn't it 1 by x? Yeah. What is the derivative of sec x? I guess it is, yeah, sec x into tan x. By the way, what is the derivative of log something? It will be 1 by the same thing, but that is not enough, multiplied by the derivative of that something part. This is called chain rule. And with that logic, let us start. Okay, A is a constant, so I'll keep the constant here. Are you able to see log something? Yes. What is the derivative of log something? 1 by the same thing multiplied by derivative of the quantity inside that circle. That will be sec x by a tan x by a multiplied by, what is the derivative of x divided by a? Yeah, 1 by a. That's it. Cut, 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 cut. So let's write it a little bit neatly. y1 is equal to tan x by a. Now what do we need next? Yeah, we need to find y2. So y2 is given by, so tell me please, what is the derivative of tan something? I forgot to ask earlier. No problem, I'm sure you're good with derivatives. So tan something, the derivative is sec square the same thing multiplied by 1 by a, isn't it? That's it. Time to plug in everything inside the formula. So our radius of curvature at any point, rho, is given by, come on, tell me the formula, 1 plus y1 square, so tan square x by a, the whole power 3 by 2, the whole divided by sec square x by a times 1 by a. I don't know how many of you are very good with laws of indices. For some special students, I am writing something here. Suppose we have a power m, the whole power n. Then this m and n will get multiplied. So look at this. What is 1 plus tan square x by a? Tell me. What is 1 plus tan square x by a? Yeah, it is sec square x by a. The whole power 3 by 2. Okay, we have to divide by something, so I am going to multiply into a by sec square x by a. So let's apply this rule here. So rho is equal to sec cube x by a. You got it right, 2 and 2 gets cancelled and there will be cube into a by sec square x by a. Cut, 1 will be gone. So what's the radius of curvature at any point on the curve? It will be sec x by a multiplied by a. So that's it. That's it. That is a very small problem, but that is a very good problem to start. Okay, now let's do one more problem and wind up this video. So please write the second question. Find the radius of curvature. Find the radius of curvature at 1 comma minus 1 on the curve y is equal to x square minus 3x plus 1. Okay, so we want the radius of curvature at one particular point. So as always, the question is this parametric form or is this Cartesian form? Of course, Cartesian, and to be precise, it is explicit function. Explicit function means one variable will be given in terms of another variable. Okay, so just like before, let's write the formula. Come on, this time you have to tell me what is the radius of curvature at any point in Cartesian form. Yeah, 1 plus y1 square, the whole power 3 by 2 the whole divided by y2. So our job is very simple. We have to find y1 and we have to find y2. I'm sure you understood that differentiation. Now there are two options. Either you plug in all these quantities here and substitute the point, or you plug in the point here and then substitute the value. Both will work. Both will work. Okay, I think let's go for the simpler version. At 1 comma minus 1. What is our y1? So our x coordinate is 1, y coordinate, there is no y coordinate, so 2 minus 3 minus 1. Now what is y2? y2 is a constant, so it is point independent. Whether you plug in anything or not, y2 is 2. So that's it. Let's plug in row value. 1 plus y1 squared. So minus 1 to square will be 1 whole power 3 by 2 by 2. By the way, it might be or it might give you a little bit advantage if you understand some quantity to the power 3 by 2 will be a into root a. You can by heart it, or if you want the logic, I will explain. This is actually 8 to the power 1 by 2 the whole cube, isn't it? And that is actually root a the whole cube. And that means root a into root a into root a, that gives you a root a. Okay, so we have 2 to the power 3 by 2, that will be 2 root 2 by 2. So what is the radius of curvature at 1 comma minus 1? Root 2. Okay, that's it. So I'll repeat the facts once more. In curvature, what we do is we learn how to measure the bending in the curve. So curvature is basically measuring the curvishness of a curve. And we learn the fact, if a curvature is very high, the circle will be small and the radius will be small. And if the curvature is less, then the circle will be big and the radius will be big. So they are inversely proportional. And then I told you, you have to be sure with 4 concepts: Cartesian form, parametric form, polar form and pedal form. Anyway, in this video we did some very basic stuff in Cartesian and parametric. Parametric we didn't do, we just wrote the formula. So I'll be back with the next video very soon. So till then, my friends, bye.